Good day, everyone. I'm here to discuss the Chapter 7, which is the conservation of energy, specifically the situations involving kinetic friction. This topic is integral calculus related. Next slide, please. But before we proceed to the discussion, let me introduce myself. I'm Glenn B. Lagarde from CED 10301P. I'm currently second year college taking Bachelor of Education major in Sciences. If you want to know more about me, you can check it in my social media accounts. Just a quick fact, I'm 21 years old and I love learning new things, especially calculus. Next slide, please. So let's proceed to the discussion. What is kinetic friction? Kinetic friction is a force that opposes the motion of two surfaces sliding past each other. It comes into play when there is relative motion between the surfaces. Here are some common situations involving kinetic friction. First is we have the some of the example is a book sliding across the table. When you pushes the book in the table, the force between the two objects, which is the book and the table, opposes the direction of motion. Next slide, please. Next example is using the brake of a car. As we use the brake pads will exert force on the moving wheel, creating kinetic friction, slowing down the movement of the tire of car. We can also apply this concept on how the plane uses its landing gear on helping to bring the plane to a stop. Now, how should we put it as into an equation? In reality, the friction force is spread out over the entire contact area of an object sliding on a surface, so the force is not localized at a point. In addition, because the magnitudes of the friction forces at various points are constantly changing as individual spot welds occur, the surface and the book deform locally, and so on. The displacement of the point of application of the friction force is not at all the same as the displacement of the book. In fact, the displacement of the point of application of the friction force is not calculable, and so neither is the work done by the friction force. Next slide, please. So let's start to develop the equation by using the equation in the previous lesson. As you can see, the dr in this equation is the displacement of the object because for forces other than friction, under the assumption that these forces do not deform the object. This displacement is the same as the displacement of the point of application of the forces. Next slide, please. Now, we can add the integral of the scalar product of the force of kinetic friction and the dr or the displacement representing change in variable. Next slide, please. So the integral value is change in f sub k x, the changes in displacement added to the product of force. The integrand on the right side of this equation is the net force summation of F. Now let's incorporate the Newton's second law, F equals ma, then the result would be on the screen. So we dr as v dt, the scalar product obeys the product rule for differentiation. So the derivative of the scalar product of v with itself can be written. Now let's substitute the result. Looking at the left side of this equation, notice that in the inertial frame of the surface, F sub k and dr will be in opposite directions. For every increment dr of the path followed by the object, therefore, F sub k times dr is equal to negative F sub k dr. The equation will become where we have used the cumulative property of the scalar product to justify the final expression in this equation. Consequently, next slide please. In our model of for friction, the magnitude of the kinetic friction force is constant. So F sub k can be brought out of the integral. The remaining integral dr is simply the sum of increments of length along the path, which is the total path length d. Therefore, the result is presented. Next slide, please. So, ayan. The increase in internal energy of the system is therefore equal to the product of the friction force and the path length through which the block moves. In summary, a friction force transforms kinetic energy in a system to internal energy, and the increase in internal energy of the system is equal to its decrease in kinetic energy. The summation of the work of, of other forces is equal to the work, and work is equal to the changes in kinetic energy plus initial change in energy. And that's all for the situations involving kinetic friction. If you have any questions, you can use the comment section below. Once again, this is Lagarde signing off. Thank you for listening and have a great day.